Hi everyone. Hey, this is Mrs. Hanson. We're starting a new chapter today, chapter 4, called A Family of Alkanes and Cycloalkanes. Kind of the most boring, really, because there are no functional groups. They're just hydrocarbon chains, either in straight chains or with branches coming off of that chain, or even perhaps in a cyclic structure known as a cycloalkane. Nonetheless, it's a very strong, fundamental chapter in the sense that it's going to teach us a lot about naming, introduction to nomenclature, really an introduction to the term constitutional isomers. We'll look at some relative stability of these isomers as well. Draw Newman projections. We'll perform a conformational analysis of ethane, propane, butane, as well as cyclohexane. We'll draw chair conformations of these cyclic structures. We'll look specifically at the axial and equatorial bonds of the cyclohexane. If it is monosubstituted, which one is the most stable conformation? If it's disubstituted, would it be on the axial or equatorial bonds to create the most stable arrangement? When I say conformation, the most stable three-dimensional arrangement. We'll have some stereoisomers to look at for double bonds, specifically in the cis-trans. And then you'll look at some polycyclic systems as well. So all about the alkanes and cycloalkane family in chapter 4. So as we said, our chapter will be devoted specifically to what we refer to as saturated hydrocarbons. The hydrocarbons, of course, are the heart of organic chemistry, composed of hydrogen and carbon. There are no heteroatoms. Remember that vocabulary word, heteroatoms. That represented any element found in an organic molecule other than carbon or oxygen. Carbon or hydrogen. Things like oxygen, sulfur, nitrogen, so forth. Those are known as heteroatoms. These are not part of our game in this chapter. Simply straight chain hydrocarbons. They'll have substituent branches and perhaps a cyclic ring as well. So notice we're just focusing on alkanes. There are no pi bonds in an alkane. When we think about the systematic way of naming alkanes, it relies on the IUPAC system, the International Union of Pure and Applied Chemistry, and kind of looking at the step-by-step way to name an alkane. We find the longest carbon chain and make that the parent name. We then name any substituents, these branches, these alkyl groups that are coming off of that longest carbon chain. We'll use a numbering system to let you know where those branches are coming off of the chain, and then really a system of alphabetizing and prioritizing those branches and come up with the IUPAC name. So I'd like to take you through those steps, one step at a time until we get comfortable, and then we'll put all the pieces together. So, when we name an alkane, the first step, we need to identify the parent chain. And by parent chain, I mean the longest consecutive chain of carbons. So as I begin kind of discovering where the longest chain is, some of these molecules can be quite complex. And here's an example. I just start numbering. I'm going to start up at the top. 1, 2, 3, 4, 5, 6, and then I'm done. There's no room to go on, so there must be a better way. Let's try another way. 1, 2, 3, 4. What if I go down? 5, 6, 7. All right, 7 is more than 6, so that's better. Let's keep testing. What if I did, let's just start down here. 1, 2, 3, 4, 5, 6. Looks like I can come this way. 7, 8, 9. Well, here I found, just kind of trial and error, 9 carbons in that particular chain. So the longest chain, just by keep trying in every possible way and coming up with 9. Alrighty, so 9 carbons in the chain. Now I, at this point, have no idea if it's better to start counting up here and come up with 9 carbons, or to start at the bottom and head up. That's a next decision. And to make that decision, we really want to consider making those branches the lowest possible number. Sometimes when we're numbering in the parent chain, there's more than one possible correct answer. So more than one possible way that gives you the same answer. Choose the one with the most substituents attached. For example, in a compound where I have 1, 2, 3, 4, 5, 6 carbons in the longest carbon chain, and if I consider this direction, I still have 1, 2, 3, 4, 5, 6, 7 carbons in the longest carbon chain. 1, 2, 3, 4. That's where I messed up right here. 4, 5, 6, 7. Both have 7 carbons in the parent chain. So which one would I select? Only one can be correct. And the answer says, well, if I picked this first, starting at carbon 1, I have 1, 2, 3 branches coming off of that parent chain, whereas with this I only have 1, 2 branches coming off of the parent chain. You want it to contain as many substituent branches as possible. So the first choice wins because there's more substituents coming off of the parent chain. When we start numbering the parent chain, we have to commit to memory what each one of these prefixes stands for. If the parent chain contains just 1 carbon, the prefix for 1 carbon is meth. Knowing that we're using alkanes, the suffix for all of these hydrocarbons that contain no pi bonds, they're considered to be saturated, the suffix is ane. The prefix meth, suffix ane, so our hydrocarbon CH4 is called methane. If we have a 2 carbon unit, this would look like CH3, CH3, 2 carbons in that chain. The prefix is eth, the suffix is ane to let you know it's an alkane, so you hear that ethane. A 3 carbon unit, CH3, CH2, CH3, a straight chain 3 carbon unit, is known as propane. The prefix prop represents a 3 carbon unit. Here we have CH3, CH2 taken twice. I'm just going to write that out. CH2, CH2, I'm going to just put that in a parenthesis. That's a 4 carbon unit. And now you can hear that as butane. That's lighter fluid, isn't it? Butane. A 5 carbon unit, CH3, CH2 taken 3 times. That's a total of 5 carbons. And that gets the prefix pent. And we'll say that's pentane. 6 carbons is hexane, followed by heptane, octane, nonane, and decane. These I will tell you to memorize. They're just so common. These are nice to know over here, 11 through 100. We will not be drawing on a typical day anything larger than 10 carbons in the longest carbon chain. Methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. Those are the first 10 alkanes representing the prefix to let you know how many carbons and the suffix ane to let you know these are saturated, all sigma bonds, no pi bonds in these structures at all. So selecting the parent chain, we want to find the longest consecutive chains of carbons. That's going to dictate the parent name based on those prefixes we just went through. If you happen to see a cyclic structure, here's a cyclic structure where all 3 carbons are bound in a cyclic ring, cyclopropane for 3 carbons in a ring. This square represents 4 carbons, cyclobutane, cyclopentane. A 6-membered ring is cyclohexane, and so forth. The prefix cyclo lets us know that the 2 N carbons are connected to one another. Now it asks us to practice, and this is not putting the pieces together yet, right? We're just doing a fundamental skill of just practicing finding the longest chain. So I'm not naming this yet, but step 1, can you find the longest consecutive carbon chain and find what we would name that parent as? And this really is just dive in and start counting and seeing where you find the longest chain. Suppose I started right here. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, there's one idea. Straight across there, there's 9 carbons. Let me switch color and see if I can find something longer. 1, 2, 3, 4, 5, 6. If I go here, 7, 8, 9, 10. Well, 10 is more carbons than 9, so the green numbering system is so far. Let's try one more thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I get 10 carbons in that direction as well. So I don't see any other longest carbon chain at this point. The longest carbon chain is decane. We were asked which one of those is going to give us the more substituent branches. If I may, I'm just going to erase this and get rid of all those ones that we deleted as choices. I'm going to just put back 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many branches did that give us? So let's count that up. I have a methyl group here. There's 1 branch, 2 branches, 3 branches, 4 branches. All right, so that's 4 substituent groups. The other way we numbered, let's see. Just trying to redraw here. All right, so let's renumber. I think we started 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That got us to 10 as well, didn't it? How many substituent branches here? Well, I see 1, 2. Oh, no, that's wrong. This is all 1 substituent branch, right? Coming off of all a carbon 5. So that's all 1 branch, and here would be a next branch. So that's not as good as it. We want the more branches. So I was just practicing the other part of that rule that says make sure you're numbering to, if there's a tie, there's 10 carbons when I counted either direction, but I want to pick the parent chain that has the most substituent branches. And that's how we identified 4 substituent branches versus 2 substituents, and realized that the first way I numbered up above here was correct. The parent name had 10 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The parent name would become decane. Let's try some more. This is other examples from your homework. We can pick a few to work out together. Identify and name the parent. So remember, we're not naming the entire structure yet, but step 1, find the longest parent chain and name it. So here I'm just going to number 1, 2, 3, 4, 5, 6. It's the best chain. I can see that this would have a parent name of hexane. We are not yet recognizing how to name branches. We're just taking a first step and finding the parent name. Well, the second structure looks like it's interesting. Let's 1, 2, 3, 4, 5, 6, 7. If I number straight across, I come up with 7. Can I find anything else? Let's see. 1, 2, 3, 4, and I'll go left. 5, 6, 7. All right, so that's also 7. Not as many branches though, correct? So that's not as good. Let me number in red. 1, 2, 3, 4, 5, 6, 7. So I have a couple of choices there of numbering. Anyway, we're just trying to find the longest parent chain. The one with the most branches would be the correct numbering system. And did I find anything else? Oops. 1, 2, 3, 4, 5, 6, 7. That's heptane. 1, 2, 3, 4, 5, 6, 7. Heptane. Anything else? 1, 2, 3, 4, 5, 6, 7, 5, 6, 7. I just really can't find anything longer. Let's try this next one. Here I have a cyclic structure. So that looks carbon 1, 2, 3, 4, 5, 6, 7. Alrighty, that one was pretty straightforward. Cycloheptane for 7. Now let's try one more. I'm doing a little bit of your homework here. Just repetition. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. That looks like the longest, so I would call that parent octane. So really, as these molecules become more and more branched, just spend some time finding the longest parent chain by making sure you have the greatest number of substituents as well. And that's the first step in naming an alkane. Find the longest branch, and that becomes your root word. The second part of naming an alkane, especially if it's branched, is to recognize the substituents. So the longest carbon chain is represented here, kind of highlighted in this orange. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I can see that the parent is going to have a last name here, decane. I then see some branches. What these are substituent groups, alkyl functional groups here, the alkyl groups. And those are hydrocarbon branches that are coming off of the parent chain. To name these branches, we use our prefixes to represent the carbon. In other words, carbon 1 is meth, 2 carbons is eth, 3 is prop, and so forth. And is naming it as the substituent, instead of having the ane ending as if it were the parent, the ane gets dropped and you put on a yl ending if it's named as a substituent branch. Methyl, ethyl, propyl. If the ane ending is present, that tells you it's the parent chain. If the yl ending is present, it tells you that it's a branch coming off the parent chain. So we are recognizing how to name the substituents. Here is a 2-carbon branch. This will be called ethyl. This is a 3-carbon branch. This will get the name propyl. And here is a single carbon branch, so this is recognized as methyl. So find those branches and assign a name based on the number of carbons in the branch. What we then do is make sure that we've identified those branches with the YL ending. So we recognize ethyl, propyl, and methyl. And now we want to figure out whether or not we have the lowest possible numbering system, the way we selected. So the big trick here is to make sure all of those groups that you highlighted as substituent branches are numbered from the parent chain to let the reader know where you can find them. And then to ensure that they are assigned the lowest possible number when you're numbering that parent chain. Keep in mind, if we have a ring, it can either be the parent chain if it's the longest chain. A cyclohexane is a 6-membered ring, and then off of this carbon is a 3-carbon group, so you would call that propyl cyclohexane. We'll learn that no number is required here because we automatically know that at carbon 1 would be the substituent branch. If here we have a 1, 2, 3, 4 carbon chain, we could name the cyclopropyl as the substituent because the 4-carbon parent is a longer carbon chain. So the cyclic structures can be the parent. If so, you'll hear them end in ane. Or they can be the substituent. And if so, you'll hear them end with the YL ending. The parent is the ane. The branches get the YL. Identify all groups that would be considered substituents and indicate how you would name them. So remember our first step, we got to find the longest carbon chain. That takes some time just to find all the different ways to number. So I'm going to start here. 1, 2, 3, 4, 5. I'm going to go up 6, 7. I could go 8, 9, or 8, 9. More branches. I'm going to highlight. There's a branch here, a branch here, and here, here, and here. 1, 2, 3, 4, 5 different branches the way I've numbered that system. Now, when I number that, I'm just kind of thinking that I want to make sure that these have the lowest possible numbers. When we get that far and start putting all these pieces together, we're going to number them to ensure the lowest numbers are assigned to these groups. I would have a methyl substituent branch off of carbon 8, the way we have it numbered. Here is a 2-carbon branch, so that is an ethyl substituent branch. This is also 2 carbons, so that's an ethyl. Carbon 4 is a 1-carbon branch, so we're naming that methyl. And at carbon 2 is a 1-carbon branch, so that's named methyl. We have 3 methyls and 2 ethyls in those branches. Let's try another. Longest carbon chain. 1, 2, 3, 4, 5, 6, 7, 8 if I went straight across. How about 1, 2, 3, 4, 5, 6, 7, 8, 9 if I went down. So that's the longest carbon chain, not what I numbered in red. So let me erase that. We found 9 carbons going down. 1, 2, 3, 4, 5, 6, yep, 9. So the parent, and again, is a nonane. I could write that up here as well, couldn't we? Because that's the parent name, 9 carbons ending in ANE. Here I have a substituent branch, 3 carbons long. And here's the next substituent, that is 1 carbon. 3 carbons would be called propyl, and 1 carbon would be called methyl. For substituents that have more complex branches, by complex, here we have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's a long carbon chain, right? And I look up at this carbon I numbered 6 and I see 1, 2, 3, 4, and then a 5th carbon coming off of there. So this what I would call a more complex branch than a straight chain. The substituent has branching itself. Find the longest carbon chain within that substituent. Clearly here you see that would be 4. And then always start numbering from the carbon that's attached to the parent chain. When we name the substituent, a 4 carbon, of course, would be called butyl. Then I'm going to let you know that the butyl group actually has a branch coming off of carbon 2. That's called 2-methyl-butyl. The branch itself, this carbon that comes off the parent chain, is always carbon 1. When I number here, this is carbon 2. This 1 carbon branch, 2-methyl-butyl, is the name of that branch. So again, we can get more complex branching from the parent chain, but we just tackle it individually and number with the substituent group. We also have some common names that we need to learn. Common names are very helpful in finding these because they're quite common. They're going to be used to name kind of branched alkyl groups. So 2 types of propyl groups. Let's illustrate those first. A propyl has 3 carbons in it. If it is a straight chain, 3 carbons all connected to each other. That's what I'm referring to as a straight chain. All the carbons are connected in a straight line one to the other. We call that propyl. The first carbon is attached to the parent, a total of 3 carbons in that branch, so that branch is called propyl. However, if we have the parent chain connected to carbon 2 of a 3-carbon chain, we have a common name called isopropyl, and then the IUPAC name for that branch would be 1-methyl-ethyl. Now think about that. Carbon that's attached to the parent is always 1. So the longest carbon chain is the ethyl group, and off of carbon 1 is an attachment that's 1 carbon long. So I name that substituent as methyl. 1-methyl-ethyl is the IUPAC name for that branch, and the common name when we have a 3-carbon branch and the parent is attached to carbon 2 from the branch, we call it isopropyl. Iso is part of the name. It is not separated by a hyphen, just simply isopropyl. Here I could have a 4-carbon chain, or maybe I'll say 5-carbon chain, whatever, off of the middle carbon. Notice that I have 1, 2, 3, 4, 5-carbon chain. And so I have 2 branches when I do that. 1, 2. So I want to be careful that if I'm considering an iso group off of carbon 3, I could consider an iso group. However, make sure that you're still obeying the previous rules. Find the longest carbon chain and make sure it has the number of branches. And so I wouldn't call that iso. I would recommend kind of noticing that the longest carbon chain with 2 branches would have a methyl and an ethyl. So just something to consider as you're working through these examples. Don't let the other rules fall apart as we're learning new rules. Here are some examples of 4-carbon chains. If I have 4 carbons in a straight chain, and I mean that they're just all connected to one another, no branching. Carbon 1's attached to 2, attached to 3, attached to 4, that's a butyl. Here are some common names for other ways a parent can attach to a 4-carbon chain. Notice here in our 4-carbon chain, the parent is now attached to carbon 2, not carbon 1 like it was before, but it's attaching to the 2nd carbon in the 4-carbon chain. You see that called as sec-butyl. I want you to notice there's a hyphen separating sec and butyl. When we're alphabetizing, sec, meaning secondary, is not part of the consideration. We would go by butyl. Here we have a parent chain, 1, 2, 3 carbons long, and on the 2nd carbon is another methyl group. This is commonly called isobutyl, that the 2nd carbon is branched. You see that? The branching occurs at the 2nd carbon, iso. Notice please that there is no hyphen between the term iso and butyl. It is all one word. Therefore, when we're alphabetizing, iso will go by a capital I in the alphabet, but we would still go by butyl because it is secondary, is separated by that hyphen. Here is a carbon attached to the parent chain, and it's attached to 3 other carbons. So that 4-carbon member is known as tert-butyl. The carbon attached to the parent is attached to the 3 other carbons. You'll recognize that as tert-butyl. Those are the common names. Notice there are IUPAC names written underneath. Find the longest parent chain and assign it a substituent branch. Sec-butyl would be known as 1-methyl-propyl. That means the longest carbon chain is propyl, and off of carbon 1 is a 1-carbon branch, 1-methyl-propyl. 1, 2, 3. The longest carbon chain is propyl, but now coming off of carbon 2 is the methyl. 2-methyl-propyl is isobutyl's IUPAC name. The longest carbon chain is 2 carbons, so that's ethyl. Off of carbon 1 are 2 branches, 1,1-dimethyl-ethyl. That's the IUPAC name for tert-butyl, common name. Those take practice in recognizing. I can't emphasize enough the importance of drill work. The skill builders assigned to you, there's many problems waiting just to gain proficiency and speed so you begin to recognize the names of and locants very quickly. Let's identify what groups would be considered substituents and then indicate the systematic name as well as the common name for any of those substituents we find. All right, so the longest carbon chain will help us locate not only the parent, but also any of the branches. So I'm just kind of numbering left to right. It looks like the longest carbon chain is going to be 11 carbons long. It looks like just straight across. And so that means I have a branch here, that's one substituent, and I have something going on down here, that's another substituent branch. So there are two branches, one coming off of carbon 4 and one coming off of carbon 7. Let's talk about carbon 4 first. I notice that there are 3 carbons, 1, 2, 3. So it's a 3-carbon branch. All right, the total number of carbons is 3. They are not connected to each other in a row, right? So they're branched, 3 carbons that are branching. So that means it's not going to be propyl. In other words, propyl would be 3 carbons all attached in a straight line. That's not what we see. Instead of being attached at carbon 1, it's attached at carbon 2. And that's my clue that that is an isopropyl functional group, isopropyl. So that would be its common name, isopropyl. When a 3-carbon branch, the carbon 2 is attached to the parent. That's called the isopropyl group. Now, the longest carbon chain is 2 carbons, so that's ethyl. Coming off of the first carbon is a 1-carbon branch. I don't need to tell you 1 so much because there's only one choice, right? Methyl ethyl. Go back to that previous slide. Notice here is the IUPAC name, 1-methyl ethyl, common name isopropyl. That's exactly what we located here. This is 1-methyl ethyl or isopropyl. How about the green one? All right, I see 1, 2, 3, 4. So there's 4 carbons in that unit. Now the 4 carbons are not straight chains, they're branched. In other words, the carbon that's attached to the parent is at C2. Not carbon 1, or it would just be a butyl group, but it's attached to the second carbon. Now, its common name would be sec-butyl, meaning secondary carbon is where it's attached to the parent. Longest parent here, the longest chain is a propyl. Coming off of carbon 2 is a methyl. 2-methylpropyl is the IUPAC name for the common name sec-butyl. Go back a slide. That's what we're referring to here. 1-methylpropyl or sec-butyl, where the second carbon is attached to the parent chain. It's going to take some practice, isn't it? I know. When I answer that, you're just looking at the isopropyl or 1-methyl ethyl. 1-methylpropyl is sec-butyl. Common names and IUPAC names from that straight chain represented in red, the longest carbon chain. Multiple opportunities to practice. As you draw out these examples, you're looking at your homework really. Here's a carbon chain. Looks like the longest chain here is a 7-carbon unit, so heptane becomes the parent. At carbon number 4, I see a branch. This branch is made up of 4 carbons. So at carbon 4, the carbon attached to the parent chain is attached to 3 other carbons. That's what we called tert. Notice there's a hyphen, tert-butyl. So 4-tert-butyl heptane. What about its IUPAC name? We'll notice the longest carbon chain attached to the parent group. You see the longest carbon chain attached to that parent is 2 carbons, and you have methyls coming off of it. So let's go back to that slide, what tert-butyl is showing. Tert-butyl, the carbon that's attached to the parent is attached to 3 other carbons. That's exactly what we had just seen in that example, so that's where tert-butyl came from. The longest carbon chain attached to the parent is 2 carbons, 1, 2. That's where you're getting ethyl. Now off of carbon 1 are 2 more methyls, so 1, 1 dimethyl ethyl. That is your IUPAC name. So here we had a common name and an IUPAC name for tert-butyl. Well, look at this guy, all kinds of things coming off. I noticed that we have a cyclic structure that's going to be the parent chain. So cyclohexane and all kinds of branching coming off. I have a branching unit here, I'll color in green. Here's another branching unit, I'll color in blue. How about this guy? We'll color in yellow. And how about bright pink for this guy? All of those are substituent groups coming off of cyclohexane. Here is a carbon attached to the parent, attached to 3 other carbons. That's a 4-carbon branch. We recognize that as tert-butyl. Here is a carbon attached to the parent, attached to just 2 other carbons. Notice that that's attached at the 2nd carbon. You need to recognize that as isopropyl. Carbon 1 here. Here's a carbon. This is a 4-carbon unit. Let me kind of highlight those. So 1, 2, 3, 4 carbons, where the branching occurs at carbon 2. This is what you refer to as isobutyl. There is no hyphen between iso and butyl, or iso and propyl. It's all one word. And what I highlighted here, this carbon is attached to the parent. That's the secondary position. So that is what we called sec-butyl. Those will take practice, recognizing that those common names are most often used. I need to know sec-butyl, isobutyl, tert-butyl. I need to know isopropyl as well. Those common names will get us through a lot of naming problems. So let's begin assembling the IUPAC name. The carbons that are in the parent chain are going to be numbered. And the way that we number them is to ensure that the lowest number possible is given to the branches. So for instance, I have a 2-methyl pentane, where at carbon 2, I have a methyl group branching off, 2-methyl pentane. Notice that I use a hyphen to separate a number from words. Here is an example of 3-methyl pentane, the branch of the methyl coming off carbon 3. 2-methyl pentane shows there's a methyl group coming off of carbon 2. 3-methyl pentane, I hear that 3 telling me that methyl comes off of carbon 3. If one substituent is present, make sure to number the parent chain so that the substituent gets the lowest possible number. This we said would be 2-methyl heptane and not 6-methyl heptane. 2 is a lower number than 6. When multiple substituents are present, number the parent chain to give the first substituent the lowest number possible. So I have a 7-carbon parent chain. I'm going to number from left to right so that I hit this first substituent. And if I had numbered right to left, I don't hit the first substituent until carbon 3. 2 is a lower number than 3, so number left to right to hit the branch and give it the first, to get the first branch the lowest possible number. If there's a tie, then number the parent chain so that the next locant gets the lowest number possible. Let's talk about that. Here's a 7-carbon chain. I have a branch at carbon 2, a branch at carbon 3, and a branch at carbon 6. Those are all methyl groups. So I would number this 2, 3, 6. One possibility. If I numbered it left to right, here's a branch at carbon 2, here's a branch at carbon 5, here's a branch at carbon 6. So see how there's a tie in the first position? Either direction got my first branch at number 2. So then I go look at the second substituent group. 3 is a lower number than 5, so I must number from right to left, making sure that I'm using the lowest possible system of numbering for all of those substituent branches. If there's no other tiebreaker, then assign the lowest number alphabetically. If I numbered this system in a 5-carbon ring, at one end is a chlorine and at one end is a bromine. B beats out chlorine in the alphabet, and so it will get priority. You would name this 1-bromo, 5-chloro, pentane. The alphabet wins if all other tiebreakers don't separate them out. Same rules apply if you're using cycloalkanes. Notice that I have carbon 1 and carbon 3. So 1, 1, 3 would locate all 3 of those methyl groups. And that would be better than saying 1, 3, 3. A 1, 3, 3 is of higher numbering than a 1, 1, 3. Notice that second position becomes the tiebreaker. Alrighty. So, repeating myself, to assemble the name, put the number and name of each substituent before the parent in alphabetical order. So remember, a hyphen separates numbers and letters. A comma separates numbers. So for instance, is making something up. 1, 3, hyphen. That would have to be tri, right? Trimethyl hexane. I made that up, but we get an idea that commas separate numbers, hyphens separates numbers from letters. Alrighty. A prefix is used, di, tri, tetra, penta, if multiple substituents are identical. Tell me how many there are. Remember, each substituent gets its own number. So even if I have dimethyl, I have to tell you where both are, even if it's on the same carbon, 1, 1, 1, 2 if they're on different carbons. But don't use the di or tri as part of the name when alphabetizing. So dimethyl, still with an M. Isobutyl goes by the O. There is no hyphen in there. Sec-butyl goes by the B because of the hyphen. It's not part of the same word. That takes practice. Following the rules, we name the compound by assembling the pieces. I have a cyclic structure. At carbon 1, I see a substituent group. We called that tert-butyl. The carbon attached to carbon 1 is attached to 3 other carbons. That's tert-butyl. Here I have a ethyl group at carbon 2. At carbon 4, there is a methyl and another methyl right on the same carbon. So I'm locating and finding with names all of the substituent branch. The parent name, cyclohexane. Carbon 1 is tert-butyl. Carbon 2 is an ethyl. Carbon 4 has 2 methyl groups, so you see that 4, 4, dimethyl. Alphabetize. Butyl, ethyl, methyl. That's the alphabetized name of those substituent branch. Then I tell you where they're located. Remember, a hyphen separates numbers from letters. 1 tert-butyl, 2 ethyl, 4,4 dimethyl cyclohexane. These get fun, don't they? Identify the parent, identify and name the substituents, number the parent chain, assign a locant to each substituent, that's the number. List the numbered substituents before the parent in alphabetical order. You're going to practice with Skill Builders 4.4. The Skill Builders is going to allow you the repetition to gain proficiency and speed. Pause your video and try some of these out, and when you're ready, come back and we'll share some answers. Name this compound. What's the longest branch? I find 8 carbons if I numbered that direction. Is there anything better? I don't know. I got to keep practicing. How about 1, 2, 3, 4, 5, 6? Nope. That might be it, right? A 4. Yeah, I think we've hit it right off the bat. 8 carbon chain there. So I numbered in green to find the parent chain. So now I know the last name is going to be octane. What do we have for branches? Here I have a methyl. Here I have a methyl. And here is a 1, 2. So that's an ethyl. Oops. So lowest numbering system was achieved. I wouldn't be any better off. 1, 2, 3, 4, 5. It's before carbon 5 before I hit the first branch there. So that's not good. I think we hit it right off the bat. There's 8 carbons at carbon number, remember, alphabetized. So E gets the priority. At carbon 4, we have an ethyl. Separate the words and the numbers by hyphens. What's next? Comma, let's see, at 2, 3, we have dimethyl, all leading into the parent name of octane. How does that match? Are we right? For ethyl, 2, 3 dimethyl octane. I think we did it. Want to try another of your homework? Let's see. I'm just going to dive in and guess. 1, 2, 3, 4, 5, 6, 7, 8. So numbering that, here's a methyl. Here's a methyl. And this is a methyl. This numbering system would give us 3, 5, 6 for those locants. Let's try another way. Let's go the opposite way. 1, 2, 3, 4, 5, 6, 7, 8. 3, 4, 6. Oh, that's better, isn't it? Numbering from left to right, as I did in green, has the tiebreaker there in the second position, the lowest possible number. So that's going to win, isn't it? These are all trimethyl. So at carbon 3, 4, and 6, separated by commas, separate numbers by commas, numbers from words with a dash. So 3, 4, 6, trimethyl octane. Want another one? Let's see what we have. Okay, I'm going to count. I don't have any idea. 1, 2, 3, 4, 5, 6, 7. There's one choice. Let's count another way. Let's see, 1, 2, 3, 4, 5, 6, 7. I count 7 in either direction. When I consider, let's say, counting in green, I had 1, 2 branches. And if I counted in red, I only have 1 branch. That's all that. So the correct numbering system wants the greatest number of branches. And so to get the greatest number of branches, we're going to number this direction. 1, 2, 3, 4, 5, 6, 7. So I count 7 there. More branches. All right, so now let's find, this is an ethyl. This is a methyl. And I have it lowered numbered first, but we're going to alphabetize when we name. So 3-ethyl. Then we have 2-methyl. And the longest parent chain was 7, so that's heptane. 3-ethyl, 2-methyl, heptane. We're doing great. Did you work ahead? You want to try one more? Oh, that looks fun. All right, so golly, we want the most branches. So if I had called this the parent chain, the 6-membered ring, I only have 1 branch. And that's coming off of carbon 1. Well, that's certainly not going to be the most branched. So that's going to end up being a substituent. So I recognize that as cyclohexyl as the name of the substituent branch. Let's see what we find. 1, 2, 3, 4, 5, 6, 7, 8. You finding 8 carbons? At carbon 2 is the first branch. That's better than going left to right where it would have been carbon 3. This is an ethyl. This is a methyl. Here's another methyl. All of those branches getting labeled. So alphabetize. Cyclo is the letter C. That's our first letter in the alphabet. So 2-cyclohexyl. The YL ending, naming it as an alkyl group, a functional group coming off of the carbon chain. Then what do we have? The ethyl then comes in the alphabet. So at carbon 4, we have an ethyl. Then we number 5, 6, telling you that there's 2 methyls. So 5,6-dimethyl. And then what was it? Octane. 2-cyclohexyl, 4-ethyl, 5,6-dimethyl, octane. Beautiful work. I wanted to do one with you because in your homework you'll also be asked to go the opposite way. Take the name and draw the structure. What would a bond line structure look like for the compound 3-isopropyl, 2,4-dimethyl pentane? So what I'm going to do is just kind of start with that parent and show a 5-carbon chain, and then once I get the connectivity figured out, then I'll be able to kind of draw the line structure from it. But I want to see what's attached where. Carbon 3 has an isopropyl, so that means I have a group such as this 3-carbon branch where the attachment is from carbon 2 back to the parent. Carbon 2 and carbon 4 have a methyl in a 5-carbon chain. All right, so 1, 2, 3, 4, 5 carbons in the parent chain. Carbon number 2, there's a methyl. Carbon number 4 is another methyl. And at carbon number 3, we have an isopropyl group coming off. The carbon leading from the parent is at carbon 2, and then you see the branch come off here. We could have started this way. 1, 2, 3, 4, 5. That's just as lovely. The isopropyl and the methyls. That's just the same thing, but flipped. Cool. Here we have a 6 carbon chain. For ethyl, 2-methyl hexane. So at carbon 2, we'll have another carbon coming off. At carbon 4, we will have a 2-carbon chain coming off. So that's kind of the connectivity to turn that into a line structure. 1, 2, 3, 4, 5, 6. There's a 6-carbon chain in that zigzag fashion. Carbon 2 is a methyl, carbon 4 an ethyl. That's it. You're doing great. I'm going to stop the video here, give you a rest, come back because we still have more practice. We still have to go through bicyclic compounds for nomenclature yet, but we need a rest. Let's pause and come back when ready.